Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lessons, we've covered Unit 1 and Unit 2. Today we'll cover Unit 3, and of course. And Unit 3 is a little bit different than Unit 1 and 2, of course, because it is something it is about something that is very interesting. And of course, it is basically about, you can say, vibrations and waves here. So basically, this is one of the topics that is very interesting because you'll be like daily dealing with phenomena or situations where you are basically, let's say, encountering with vibrations and waves, for example. Let's say considering with, for example, this video recording, let's say when you are hearing me, basically there is a sound wave that you hear me, of course. And of course, regardless to this, like what happens in between, of course, whether this, while it is broadcasting, that's a different story. But when you hear me, of course, you are hearing me because of vibration and sound, of course. Or you can say the speaker vibrates and this vibration will change into a sound, and this sound will be transferred into, or we can say the sound is transferred through the air, and this is how you can hear me basically. Okay, so far we talked about so basically in this chapter or in this unit here, we have a different type of motion. So far we've covered translational motion, we've covered rotational motion. This time we're going to talk about periodic motion. And one of the examples of periodic motion that we are dealing with today is simple harmonic motion. So basically that is the concept for this, or the main concept that we will be going through in this lesson. And of course there are other types we can say, or we will be dealing with some other concepts later on. So what are the preview of this chapter? So of course we will be going through simple harmonic motion. That is basically section 1, and then after that section 2. By the way, we have 4 sections in this chapter or in this unit, measuring simple harmonic motion. How are we going to measure the motion of the simple harmonic motion, or let's say factors like amplitude, like period, the time, for example, and of course the frequency as well. And then after that, we will talk about the properties of waves. That'll be wave motion, wave type, and once again, period, frequency, and wave speed as well. And then of course we'll wrap it with wave interaction, wave interference, and of course reflection of waves and standing waves. So the first thing to go through, or the first concept, is going to be basically we will go with simple harmonic motion, like we've mentioned. So what is simple harmonic motion? Before we cover that, of course, we need to understand a few things here. We have periodic motion, we have oscillation. So what is the difference between periodic motion and oscillation motion? I think it is pretty obvious from their names, okay? So periodic motion, you can say it is the motion of something, or refers to any motion that repeats itself, you can say, at regular time intervals. For example, if I keep moving forward and then backward and then forward and backward, that is basically something, it can be called periodic motion. That means I'll repeat my motion at regular time intervals. For example, in 1 second I go forward, and then the other second I'll go backward, let's say. So this is something called periodic motion. It repeats its motion, or back and forth, or vibration at regular time intervals. That is called periodic, okay? Now we have another type of motion that is called oscillation motion, right? Or oscillation. So oscillation is a little bit different than periodic. And what is the difference between this? Or what is the difference with the oscillation, let's say? We can say oscillation is the repetitive back and forth movement, you can say, of an object around the center point or equilibrium. So when something moves back and forth, let's say, or this back and forth movement of an object about an equilibrium point or central point, that is called what? That is called oscillation. So let's make a difference between periodic and oscillation. Of course, we will go through some examples as well. I don't know, something wrong today. Okay, so once again, we have periodic motion that you can say it is a motion, or you can say this motion would be repeated at regular time interval. Okay, that is one. If it is oscillation, you can say it is a repetitive, something that repeats. You can say repetitive back and forth movement about an equilibrium or central point. You can say central point or equilibrium here, it means the same thing here. Now to understand this more, let's go through some examples, yeah? The first example that we have is a playground swing, let's say. Now in order to understand this better, of course it would be best if I, let's say, show you some animation as well. Okay, so like explaining these with few motions, let's say, and then of course it makes more sense to go through this one here. So the first one that we have is basically a playground swing here. So remember, we have two types of motion. We have periodic, and of course we have oscillation. We said periodic, it basically the motion will be repeated over regular time intervals. So now this swing here, you can see that, okay, that every, let's say it takes 1 second to go forward and 1 second to go backward. So this is, we can call it periodic. What about oscillation? We said oscillation is basically a repetitive back and forth movement, yeah? So if this is the, for example, let's say the original movement here, we can say that this child is swinging about the equilibrium position or equilibrium point here. So we can say this, or the motion of a swing or swinging basically has both type of motion. It is both periodic. Why it is both periodic and oscillation as well. It is periodic because it repeats its motion at a regular time interval, and of course it is oscillation because it moves back and forth about an equilibrium position, you can say. That is the first one. So we can say it is both type of motion, both periodic and oscillation as well. Another one is basically the pendulum of a clock. That is also, you can say, it is almost like the same or even more accurate than the swing, for example. So you can see it is going back and forth. So it is periodic because, let's say, it repeats its motion at regular time intervals. So you can say this back and forth movement, it happens, let's say, at a regular time interval. That is one thing. And then for the oscillation, does it move back and forth about an equilibrium point? Yes, so it is both type of motion as well. What about the third one here? The motion of a mass attached to a spring here. Take a look here. So this mass is basically moving up and down, yes? So you can see here that this motion is going to be repeated at regular time intervals, yeah? That is one. So can I call it periodic? Yes. Why? Because this motion repeats itself at regular time interval. That is one. And second, can I call it oscillation as well? The answer is yes, because basically this spring is basically, you can say, moving or vibrating about the equilibrium position here. So if my fingertip is basically the equilibrium position, this mass is going to move away from this and then let's say get closer to this, or you could just say it is moving up and down about this equilibrium position here. Okay, now we have another type of motion, the swinging motion of a trapeze acrobat here. This person would be something like the swing, yeah? So you can see that this motion or back and forth, that is both periodic, you can say, and is also oscillating at the same time as well. But look at the differences here. Now, we do know that Earth moves about the sun. That is true, yeah? So you can see that this motion repeats at regular time interval. So can I call it periodic? The answer is yes. Why? Because the Earth moves about the sun once every year. That we all know that, yeah? So we can call this one periodic because this motion repeats at regular time interval, which you can say this motion repeats every, let's say, single year. That is one, yeah? So we can call it periodic. But can I call it oscillating? The answer is no. Why not? Does it move back and forth about an equilibrium position? No. You might say, but Mr. the sun is at the equilibrium position. No. Like, remember this, the Earth is moving about this, yeah? It is not moving at, let's say, or about this point. So does it move back and forth? It is not back and forth. So if there's no back and forth movement, then we cannot call it oscillation here. So this motion here, it is only periodic because there is no back and forth movement about the equilibrium position here. Okay, now, the next one that we have is basically, all right, the motion of the Earth on its axis. Another type of motion that we have, we do know that the Earth spins on its axis, which is basically, this is what causes day and night. But once again, we do know that the Earth completes one, let's say, spinning, okay, about itself, let's say, in 24 hours. So in 24 hours, let's say, we have one complete spinning, let's say. But here's a question. It happens every single day, yes? So we can call this one periodic because this motion happens periodically at a regular time interval, which is every 24 hours. You can say it completes one spin. That is one. But can I call it oscillation? The answer is no. Why not? Because we said in order to call something oscillation motion, it has to be moving back and forth about an equilibrium position here. So is this spinning, is there any back and forth movement about the equilibrium position here? The answer is no. If that is the case, then we can call this one just periodic motion, not oscillation. Okay, so now let's summarize this real quick. We said periodic motion is the motion of something or a body, an object that repeats, let's say, at regular time intervals. So you can see this motion, or the day and night, repeats every, you can say, 24 hours, so this is periodic. But in order to call something oscillation, it has to, the back and forth movement, or there must be a back and forth movement, a repetitive, by the way, a repetitive back and forth movement about an equilibrium position here. So there's no back and forth movement, there's no equilibrium position here, so we cannot call it oscillation motion. So you can see the differences. These are both contain, or goes to both, you know, categories, oscillation and let's say periodic, except then the last two are just periodic. Okay, so now we've learned the difference between all this, yeah? So let's get back to the main concept again, and of course now these are what we have, or what we went through, yeah? So we said, for examples for periodic motion and oscillation, or playground swing, pendulum of a clock, motion of the mass attached to a spring, the swinging motion of a trapeze acrobat, the motion of the earth, that is, remember, it is periodic, and the motion of the earth, once again, it is periodic, not oscillation, because there is no back and forth movement here. So in order to emphasize on this more, take a look at the definition, of course, then it will be very easy to make a difference between the two. Now, at the equilibrium position, speed reaches maximum. So what happens when we have a spring, okay, and this spring is oscillating back and forth, let's say, horizontally. Okay, so there are some factors involved here. Okay, we can say the motion of this spring is both periodic, and of course it is oscillation as well. Now, let me show you one more, let's say, GIF or animation, whatever you like to or prefer to call it. So take a look, let's go forward a little bit, fast forward. Take a look at this one here. So we have basically a spring here. This line represents the equilibrium position, yeah? So what happens if I, let's say, compress the spring? Of course, the spring will compress, then, of course, there is a force, basically restoring force, try to push the spring. So if I push the spring this way, okay, you know that the spring will be compressed, but there is a force this way, yeah? What if I stretch the spring into this direction here? So we can, let's see. We can pause this for a second. Oh, very good. So take a look at what I have in here, guys. This is basically called equilibrium position here, or you can call it X, or displacement is 0. So what happens if I extend the spring just like you see here? Let's move this one downward a little. What happens if I stretch the spring here just like you see here? So in this case, you can see that X is maximum here. That is the displacement, because we stretch the spring. But what happens to the force? Like what happens, what do you feel here? You feel that there is a force trying to bring this mass back to the equilibrium there. So we can say there is a force acting, for example, on the mass here, but the direction of the force is basically to the opposite direction. So you are stretching into this direction, but the force that is trying to bring it back is basically towards the other direction here. So based on this, we can say that the force and the displacement are, remember this, directly proportional in terms of magnitude. In another word, the more you stretch, the bigger the force becomes. But their direction will always be opposite to one another. In another word, once you stretch the spring that way, the force will try to bring it back to the equilibrium. Or if you're trying to compress it, let's say, then you are basically making the displacement, or the direction of the displacement is this way, but the force will be towards the other direction. So we can say the force, and let's go back to this one more time. Okay, so we can say, let's go back and clean this. So we can say the force is basically directly proportional to the displacement, but these two are in opposite direction here, okay? So these are, when we say directly proportional, that is in terms of the magnitude, but in terms of the direction, of course, they will be inversely proportional. So, but there are a few other factors that are concerned here, guys. Listen, if the force is at maximum, what do you think about the acceleration? Of course, the acceleration will be at maximum as well. If that is the case, then what about the potential energy? If that is the case, then of course, or elastic potential energy, we can say elastic potential energy will also be at maximum, because you can see that is stretched the most, that is also maximum. What about like the moment before we let it go? How about if I just explain this one? Now, I want you to watch this one more time before I explain this one like in full detail. So let's do this one. Take a look here. I want you to think of this one, this equilibrium position. This is maximum displacement, and this you can say maximum displacement in the opposite direction, you can say, or still away from the equilibrium here. Okay, so now after you saw this, okay, so let's get back to this. Now it is time to go to this. So here's what we have, guys. Okay, we can go back to this and this. Okay, so I want you to watch this one here. We're going to emphasize on this a little bit. Okay, so take a look here. Let's say we have a spring in 3 different situations, okay? So let's say this is a spring. Here is being stretched up to this point here, okay? And let's say this is the equilibrium position, or where x is equal to 0. What does equilibrium position means? That means a point where x, for example, if this is equilibrium position here, that means x is 0 here, okay? That means the spring is not stretched or compressed. So at this point here, if this is, let's use red line here. So let's say this point here is the equilibrium position. I think it was too much. So let's go back. Let's just keep it here. So this point is basically where x is 0. Displacement is 0. So if that is the case, let's use this one. And of course, now we're going to make a table, but here we're going to take 3 different situations, okay? So that is first situation, we can say. And this, let's use blue again. And this is second situation, let's say, okay, where the spring is at equilibrium here. Okay, and then of course we have, this is basically where x is 0. I think it's too much compared to the other one. So let's make it small enough so that it matches the second one too. Okay, so blue again. So this is second case. And here's, let's say, where the spring is at equilibrium. So x is 0 basically here. And then of course we're going to use or take another case where the spring is compressed this time, okay? The spring is compressed. You can see here, this is x is 0. And this, of course, if this is x is 0 here, then I think we can make this one a little bit shorter here. So at this point here, x is basically, if this is x at this point is 0, you can see x is, it has a value, you can say maximum, but of course at the opposite direction here. So here's what we're going to do. What we're going to do is we're going to make a table for phi factors here. So we can say, let me use straight line perhaps. Let's see if we can do that. So let's say 1, 2, 3, 4, 5, and 6 as well. I was hoping to get some straight lines, but I didn't. Okay. So let's change this back to normal. Okay, 1, 2, 3, 4, 5, 6, 7. All right, so here we can say we're going to talk about the displacement. How about the displacement first, yeah? We can go with the force. No, with the displacement maybe first. Okay, so we'll say displacement. Okay, we'll say the force. And then if that is the case, then acceleration here. And then elastic potential energy, we can say. And of course, we can have, let's say, okay, we'll ignore the theta for now because we have a spring. We don't have a pendulum. We have speed. And of course, we have kinetic energy. And we have momentum as well, which is equal to mass times velocity as well. So take a look at the first case, guys. Take a look, yeah? Here, x, you can see if this is x at equilibrium. So at this point here, x is in this direction, yeah? So we can say maximum displacement, yeah? So x at this point is basically at maximum displacement. If that is the case, then the force is in the opposite direction. But of course, the force will also be at maximum as well in terms of magnitude, yeah? In terms of direction, you can see that it is in the opposite direction. So we can say the force at this point is also at maximum. But if that is the case, using Newton's second law of motion, force equal to mass times acceleration. If the force is at maximum, of course, the acceleration will be at maximum as well. So we can say the acceleration is also at maximum, if that is the case. Yeah? What about elastic potential energy? You can see if x is at maximum, then of course elastic potential energy can be at maximum as well. And of course elastic potential energy, we have few questions or equations to calculate that, of course, but it concerns x, let's say. So if that is the case, then we can say elastic potential energy is also at maximum here. Now, this is the point where we stretch the spring, but remember this, we haven't released the spring or the mass yet. So if that is the case, we just stretch the spring up to this point and we hold the mass, let's say. If that is the case, you can see that there is no motion, yes? Very good. So if that is no motion, or you can say no movement, that means the velocity or the speed is 0 meter per second. You can say this is in Newton, this is in, you can go with meter as well, this acceleration meter per second squared, and then potential energy, that is in joule, you can say, and kinetic energy, that is basically, we can say kilogram or joule as well, okay? And then for momentum, that is basically kilogram meter per second, meter per second. Okay, so forget the unit for a second, yeah? If there is no motion, that means the speed is or the velocity is 0, yeah? What about the kinetic energy? If the speed is or velocity is 0, let's say for the kinetic energy, that is speed, so the speed will also be 0. And I mean, the kinetic energy will be 0 as well, because kinetic energy equal to 1 over 2 mass times velocity squared. If no velocity or speed, then no kinetic energy. But if there's no speed, we can say the momentum is also 0 in this case. So this is for the first case, yeah? What about for the second case when, remember this, so we release the mass so that the mass is now basically is going back to the equilibrium position here, guys. Remember this, yeah? At the equilibrium position, remember if you have a spring, you stretch it and you let it go. So you let it go. Now this spring, of course, it is springing back, or you can say it brings the mass back to the equilibrium position. So you can say at this point here, right here, basically, we can say, okay, we said before that if the displacement is 0, so what about the restoring force here? The restoring force will be 0. Why? Because there is no stretch at the equilibrium. So we can say, or before that, the stretch or the displacement is 0. Okay, remember this, the displacement is 0. If the displacement is 0, now the force will also be 0, because later on we have a question, Hooke's law says, F equal to negative kx. So if this is 0, of course this one is also, or will be 0 as well. That is the restoring force. If the force is 0, guess what happens to the acceleration? The acceleration will also be 0. If that is the case, what happens to the elastic potential energy? Once again, elastic potential energy related to the displacement. And of course, if displacement is 0, then that means the elastic potential energy is also 0 as well. By the way, the elastic potential energy, you can go with 1 over 2 negative kx, or what was it? Yes. So if I remember correctly, elastic potential energy 1 over 2 kx, yeah? That is one of them, or you can say, it was fx, okay? Or in this case, 1 over 2 kx squared, yeah? That is also the two equations that we can use for elastic potential energy, but you can see that it depends on x, yeah? So if x is 0, then the elastic potential energy will also be 0 as well. Okay, now going back to, if that is the case, remember this, guys. So we let this spring to move pass through the equilibrium, but imagine what happens when you let the spring go. At this point here, or when it, for example, it has a lot of momentum, you can say, yes, or let's say Newton's first law of motion. If something is moving, it tries to keep moving at the same speed, or let's say at a constant speed, if it is not bothered by any external forces, let's say. So if that is the case, then of course for the velocity at the equilibrium, because it was moving, so we can say at equilibrium, the velocity here is going to be maximum here. Okay, so let me tell you something, guys. So whichever the values that were maximum, now they are going to be 0 here. Whichever 0, these are all going to be maximum here. So this is for simplicity. If velocity is maximum, kinetic energy will also be maximum, yes? Why? Because kinetic energy, like we said, it is equal to 1 over 2 mv squared here. So if this is maximum, so the kinetic energy will be maximum. If velocity is maximum, then of course the momentum will be maximum as well. Okay, now after this, now this mass of course is going to move past the equilibrium, and now it is going to compress the spring here. If that is the case, this is where we get at this point here. So this is the point where x is maximum, but that is in the opposite direction. What about the force? Then the force will also be maximum, but remember this time the force is in opposite direction. So we kind of like compress the spring this way. Take a look at the direction of the displacement and look at the direction of the force as well. So you can see here, if the displacement is maximum, then the force will be maximum as well. So what happens to the other factors? Let's take a look. So if that is the case, we can say x is maximum, okay? And then let me keep using the same word. Perhaps it would be better, because there is a reason why I want to use the same. Okay. All right, so we said this one, or the displacement is basically maximum. If the displacement is maximum, so it is the force, which is maximum. Let's write it, okay? So maximum, okay? And if the force is maximum, the acceleration is also maximum. If that is the case, what about the potential energy? I mean, elastic potential energy that is also maximum. At this point here, guys, listen, this is the point where you keep pushing the spring until this point so it pauses or hold the mass, let's say, for a second, yeah? If that is the case, then the velocity or the speed is going to be 0 here. The kinetic energy is 0. Just like take a look at the trend here. These are maximum, now they are 0. And then if they were 0, they are going to be maximum again, yes? Okay, and those that were maximum, they're going to be 0 again, and the same for the momentum here. But there are some other cases which I want you to be aware of as well. So what happens, for example, let's say when the mass is, let's make this one smaller a little bit so we can erase these without erasing any important parts here. Okay, so what happens, for example, at a point in between, let's say, this mass is restoring here, so it is going back to this point here. So we want to know what happens to the forces, to the displacement, to the velocity when it is something in between. This is x at maximum, you do know that, yes? And this is x at 0, you can say, or displacement is at 0. What about at a point in between? Let's say something like this here, for example. Okay, this is the equilibrium position, okay? And this is maximum, let's say, displacement. We want the mass at a point here, let's say. Okay, so take a look here. So what happens to each one of these factors, guys? So take a look here. What we have in here, at the first place, we had x at maximum. And this is basically, this is maximum, this is minimum. This is something in between. So you can see here, x is going from maximum to minimum. So at this point, what do you think will happen at a point here? Can we say that the displacement, it is decreasing? That makes sense, yeah, because you are at this point, you are about to go back to the equilibrium. So if you are at this point here, your displacement is about to decrease, or it is decreasing because you're about to reach the equilibrium here. So we can say at a point here, at a point right in the middle, let's say, let's keep this one the same. So at a point here, you can say that the displacement is basically decreasing here, okay? So it is not maximum, not minimum here. At a point here, we can say your displacement is basically decreasing. Decreasing, let's say, and so that it is about to get to 0 here. So we can say it is decreasing. Decreasing, okay? So how about if I just draw an arrow towards the 0, that means it is decreasing. What if that is the case, what do you think will happen to the force? The force is not at maximum, not at 0, but it is about to reach, let's say, equilibrium, yes? If that is the case, then we can say the force is also at a point here, guys, watch this, at this point right here, this is equilibrium, okay? And this was F maximum here, not 0, F maximum. So this is something in between, yeah? If that is the case, I think it is a little bit messy now. I want you to focus here. If that is the case, then, of course, the force is decreasing from maximum to 0 here. What about the acceleration? So we can say the same thing for the acceleration. What about for the potential, elastic potential energy? That is also the same. But look, what happens to the velocity, okay? Regarding the velocity, it is, let me just redraw this one a little bit nicer. Okay, so regarding the velocity, where's this as well? We can draw this one more time. So this is at equilibrium. It is a little bit more than that. You can see right here. Okay, this is the mass basically, and it is restoring. So this is x, where x is 0, you can say. So at this point here, this is where x was at maximum here. Okay, and of course F was maximum and all that. So at a point here, V was 0 here, V is maximum here, yeah? What about at a point here? At this point, it is going to, you can say, increasing until it reaches maximum here as well. So we can say that for the speed, it is going to increase at that point here, increase to maximum here, okay? That would be for this one. What about kinetic energy? That is the same thing, and of course the same thing. So look at the trend, guys, what happens. For those that were maximum, they are going to decrease anywhere in between, let's say. This is maximum, this is minimum. Anywhere in between this, it is going to decrease towards 0 here. Okay, but for the other three factors here, you can say anywhere in between, they are going to increase to become maximum here. So what happens at a point here after we pass the equilibrium? Now that is also important for you to know. At a point, let's say after, so let's say, I don't know, let's call this one A. That was supposed to be number 2 here. And let's call this one B here, okay? Let's call this one, how about if we move this one, let's say, see if we can do that. Yes. Okay, let's call this one B here. At B, let's say, but make it a little bit closer. This is B. So we want a point not at minimum, let's say, not at equilibrium, not at maximum displacement, yeah? Somewhere in between here. So that is the case. Let's just do somewhere here. Okay, we can extend this one for the sake of the explanation just a little bit. So you can see the difference. Now we want blue. So let's get back to this. Okay, so blue. Okay, so just for the sake of this, we're going to extend this one a little bit. So here's, let's say, equilibrium, x is 0. So this is x is maximum. So we don't need this one. Okay, and then here we are basically somewhere in between equilibrium. Okay, this is equilibrium. And this is maximum. So we are, let's say, at this point right here, but we are about to go to the equilibrium. So if that is the case, you can see that once it is compressed, x is, or displacement, it is about to increase. You can see here, it was at 0, then now it is going to increase. Increase to what? Increase to maximum, because at this point it's going to be maximum. What about the force? If that is the case, then of course the force is going to increase to maximum as well, because the more you compress, the bigger the force it gets to, because we said these two are directly proportional in terms of the magnitude. So bigger displacement, bigger force, okay? What about the acceleration? So the bigger the force, the bigger the acceleration. That means this one is also about to increase to maximum, yes? Or it is increasing, you can say. What about the potential energy or elastic? That is also increasing, you can say. But what about the speed? We said speed at, or the velocity at equilibrium, it was maximum, yeah? So as if it goes, as it go, for example, as it becomes compressed more and more and more, the spring, of course, you can say it becomes harder because there was a restoring force comes in and makes it harder for you to move or to push the spring furthermore. So you can say the speed will decrease here. So you can see from maximum at equilibrium, then the speed is going to decrease until it becomes 0 at this point here when the x or the displacement is at maximum. If that is the case, what about the kinetic energy? It is going to decrease from maximum at equilibrium to, let's say, to minimum at the maximum displacement here, yeah? And of course, the same thing for the momentum, which is also going to increase until it becomes 0 here. So the bottom line, I can erase all this. All right, I don't know if you can take a screenshot if you want to, but what I want to do is this, yeah? Erasing all this. Let's see if we can do that. Erasing all this, and then I'll try to demonstrate or explain all this one more time, but of course, a little bit differently here. I'll use one diagram to do all this, yeah? All right, I think, oh, it didn't work. Okay, so I'll just erase this one using this. So we'll use one spring, but of course this time instead of drawing two different springs, we'll use points on the spring here. And I hope if you understood what we have explained previously, then of course this will be easy for you to understand as well. So here's the spring, let's say. We'll make it long enough so that we have time to put, or enough space to put all these points at different places here. So let's say this is the mass, of course. Okay, and let's say this is the equilibrium position here. Let's call it whatever the point that you can call it, yeah? So let's say x is 0 here. We can say x is, or displacement is max at this point here. And of course, once it is compressed, let's say the x will be at this point here. That is also maximum, but of course in opposite direction here. This is the direction this way. The other direction is this way, basically. What about for the forces now? So we can add points now. We can say, let's use different color. So let's say we have point A, we have point B, we have point C here. We said at point A, because we stretch the spring, so the force the displacement first, the force, the acceleration, the elastic potential energy. At this point, these are all will be maximum. But the mass doesn't move yet, yeah? So what about the velocity? What about the velocity or the speed? You can say the kinetic energy and the momentum. These are all zero. Why? Because there's no motion, no speed here. Okay, now at point B, this is at equilibrium. So what happens when you let it go? This spring is going to move, let's say, become, where the speed increases until it becomes like, slides real quick at the equilibrium and then goes all the way at C here. So once again fast and then slow down here. If you can see the motion of my hand when it passes through the equilibrium, watch this, yeah? So this is the point where it keeps stretching at this point. So increases until go past like real quick, and then it gets slower and slower until it stops here. Then becomes faster and faster, it keeps moving fast, and then it slows down on the other hand, or on the other side, you can say here. Okay, so these are the points basically. All right, so these are at point B, you can say the force is zero because there's no displacement. Displacement is zero, force is zero, acceleration is zero, elastic potential energy is zero, as you can see here. At this point, these are, but the velocity is maximum, the kinetic energy is maximum, the momentum is maximum here. At point C here, again, the displacement is maximum, force is maximum, acceleration is maximum, elastic potential energy is maximum, yeah? What about a point in between, let's say, we have, let's say, at a point here. So after you let it go, for example, at this point here, let's call it point D here, okay? At point D, it is moving, and it is about to go to equilibrium position here. So at this point here, you can see that it is not at maximum, it is not at minimum, it is in between, yeah? So for the displacement, remember this was maximum, okay, this is minimum. So at this point, it is decreasing from maximum, and it is about to move to, the equilibrium here. So you can say the displacement is decreasing. If displacement is decreasing, the force is decreasing, the acceleration is decreasing, you can say, and also the elastic potential energy is decreasing as well. But what is increasing is the speed, the kinetic energy, and of course the momentum as well. And then after that, it goes to the equilibrium. What about at a point here, guys? So at a point here, take a look. Now from zero displacement, it is about to go to maximum displacement. So if x is increasing, all right, if x is increasing, that means the force is increasing, the acceleration is increasing, the elastic potential energy is increasing. But remember this, because the force is coming, okay, so makes it a little bit harder. So the velocity is decreasing because it was max at minimum. The kinetic energy is decreasing. The momentum is also decreasing at this point here. At a point there, of course, these will be maximum. These are zero there. So this is basically the summary of all the points that we can have at each one of these points. And I hope it was clear enough, okay? And this basically, you can see that it is neatly and nicely organized here. And I hope this helps you understand or makes sense for you to know how it is done well enough. Okay, moving on. Now we have basically, we can go through simple harmonic motion, yeah? So what is simple harmonic motion? Or you can say in simple harmonic motion, the restoring force is directly proportional to the displacement. Okay, so how do we define simple harmonic motion? Or before that, let's talk about Robert Hooke, yeah? Basically, Robert Hooke in 1678 showed that the restoring force is directly proportional to what? To the displacement of the mass, you can say, and this relationship is known as Hooke's law. So he said that if we stretch a spring, of course, and we can say that the force is directly proportional to how much you stretch the mass, yeah? So the more you stretch the mass, the bigger the restoring force is, of course, and that is based on if the limit of proportionality, or you can say the elastic limit, is not exceeded. That's a different story. But for now, just remember this. The more you stretch, the bigger the displacement, the more the restoring force. But again, these two are directly proportional in magnitude only. Okay, the more you stretch, the bigger the force get. But their direction are opposite. So if you stretch the mass this way, the force tries to bring it back the other way. Okay, so we have now simple harmonic motion. What is simple harmonic motion? We can say it is the vibration about the equilibrium position in which the restoring force is directly proportional to the displacement from the equilibrium. Okay, once again, the definition is very important. It is the vibration about the equilibrium position in which the restoring force is directly proportional to the displacement about the equilibrium or from the equilibrium. So we have an equation. What does the equation say? The equation says Elastic force, as you can see here, equal to negative kx. This force is basically measured in Newton. The x, that is the displacement measured in meter. This k stands for the spring constant. In another way, it stands for the stiffness of the spring. So the bigger the value for the k, that means the stiffer the spring. We have seen that some springs are very easy to compress, let's say, or stretch, like the spring inside a pen, let's say, or pencil sometimes, okay, if it is a mechanical pencil. But think of the spring that a car uses, for example, or the car suspension, we call it, yeah? So of course, that spring is very thick and very strong. Why? So that it can hold the mass of the car, and then it can, for example, withstand all these bumps and let's say, or whatever, yeah? Okay, so in another word, the bigger the value for the k, that means the stiffer the spring. If the spring is stiff, that means you cannot compress easily or stretch easily. It requires a lot of force in order to stretch or compress. Okay, so here's the equation. What does this negative stand for? This negative stands for, or it means that the force or the direction of the force is always, let's say, opposite to the direction of the displacement, like we've mentioned earlier. Okay, what do I mean by this? Let's say this, yeah? So like we've mentioned earlier, if this is the spring here, you're trying to stretch the spring in this direction. Let's say this is, or if this is the direction of, let's reverse the direction. If this is the direction of the displacement, then of course the force tried to bring the mass this. So you can see that these two are in opposite direction. Remember this, okay? And that is of course what it means by there. Then I did not mention the unit for k, yeah? What is the unit for k? Because sometimes you might be asked, find, or what is the unit for k? If you want to find the unit, don't memorize anything. K in this equation equal to what? Equal to F over X, yeah? So F is measured in Newton, X is measured in meter, so we can say the unit for K is Newton meter. That is the unit for the spring constant. Take a look at these study tips. These are very, very important. What does it say? It says the sign in the equation signifies the direction of the spring. Force is always opposite to the direction of the masses, displacement. The direction of the spring force and the acceleration, by the way, the direction of the force and the acceleration are always in the same direction. Or you can say if you, let's say, if the force is in this direction, of course the acceleration will be in that direction as well. So we can say force and acceleration will be in the same direction here. Now we're talking about the net force, by the way. Okay, and then the direction of the direction. Okay, we went through this one. The greater value for k, that means what? The stiffer the spring. We said a greater force is needed or stretch to compress the spring if we have a like high value or big value for k. In an ideal system, there's something very important. Once you just stretch the spring and you let it go, it swings back and forth. If the spring is ideal, what does it mean if it is ideal? That means if there's no air resistance or friction. If that is the case, then the spring will swing indefinitely. It will swing forever, okay, because there's no energy lost, okay? If that is the case, then of course we can say elastic potential change to kinetic, kinetic change to elastic, so the spring keeps swinging forever. But this doesn't happen in real world or in the lab, let's say. Why? Because there's air resistance and friction which slow the motion down until it eventually stops. And when it stops or slows down, that is called damping here, okay? Like the amplitude will get smaller and smaller or vibrate less and less until it completely stops. And then every simple harmonic motion is basically, and something also very important is this, okay? Every simple harmonic motion is periodic motion. So do you remember what was periodic motion? We said it is a repetitive, or you can say the motion, periodic motion, the motion of an object that repeats itself at a regular time interval. So if something is, let's say, moving back and forth, whether if it is a spring or a pendulum, let's say, you can see that it keeps moving back and forth. So you can say it repeats itself at a regular time interval. But can we call simple harmonic motions, let's say, or every periodic motion simple harmonic motion? No. When can we call a periodic motion a simple harmonic motion? We can say that if the restoring force is directly proportional to the displacement, and if the object, where you can say swinging about the equilibrium, and also it must be on a straight line as well. Okay, so all periodic can be called simple harmonic motion if the restoring force is directly proportional to the displacement and also on a straight, let's say, line or path. This is cancelled here. So now listen, in order to solve questions, it would be best to consider x to be negative always. So for example, of course, there's a lot of other ways where you can, for example, explain this, but in order to make it easy for you, I'll make it easy for you to get calculations correct. Whenever the value for x or displacement is given, you always make that value negative regardless to the negative that is given in the equation. So for example, let's say if x is negative 3, let's say x is 3, okay? Or 30 centimeter, that would be 0.3 meter, okay? If that is the case, then of course we'll use the equation, Hooke's law, f equal to negative k times negative 30, okay? So if the value of x is given, you always make it negative, but do not change the negative, or regardless to the negative of the equation, we can say. All right, we have these two questions are very important. That is chapter review questions. The first one says, what characterizes an object's motion as simple harmonic motion? So when can we call the motion of an object simple harmonic motion? Yeah, or what are the characteristic, what are the properties of the simple harmonic motion? So if any object or any motion has these three properties, then of course we can call them simple harmonic motion. So what are they? The first one, remember this, we said the restoring force must be directly proportional to the displacement. That is rule number one, you can say, yeah? If we want to call something simple harmonic motion, there has to be these 3 points met, yeah? The force is directly proportional to the displacement. That is first. Second, it has to be what? It has, or the oscillation or the vibration must be about the equilibrium position or point. You can say, so there must be a back and forth movement, a repetitive movement, but this back and forth movement must be about the equilibrium, not just moving forward or backward and that's it. It has to be a movement about the equilibrium. That is if it is a pendulum, or it could be a spring that moves back and forth about the equilibrium. And then the third rule, it has to be on a straight line, okay? So let's summarize all this. I said the force must be directly proportional to the displacement. This back and forth movement or the oscillation or the vibration must be about the equilibrium. And then the third one, it has to be on a straight line. Then we can call it simple harmonic motion. All right, what about the second question here? It says, does the acceleration of a simple harmonic oscillator remain constant during this motion? Is this acceleration ever zero? Explain your answer. So let's see if we can get back to the other one here. Okay, let's see if we can get it back. So I think it was yes. Okay, let's see if we can go back to this. All right, so this one here. Take a look at the acceleration here. We said here is the acceleration. At a point here, you can see that it is maximum, yeah? That is at this point here. At another point, at equilibrium, it is 0 here. So we can say here is maximum, here is 0, and of course here is, again, maximum, but in opposite direction here as well. So what about at a point here? It is in between maximum and minimum here. So can we say the acceleration is constant? Does it remain maximum always? Does it remain 0 always? No, all right? So you can see that the acceleration keeps changing from maximum, decreases until it becomes 0 or minimum, and then it keeps increasing until it becomes maximum again. So the acceleration does not remain constant, it is always changing, yeah? From maximum to, let's say from maximum to minimum, or you can say to even 0 here. So you can see the answer is no. Is the acceleration or does it remain constant during the motion? No. Is the acceleration ever 0? Of course, yes. So for the first part, no, the acceleration does not remain constant because it changes throughout the oscillation. Does it ever become 0? Yes. When will it become 0? When it is at the equilibrium, and of course it is maximum at the two extremities, or you can say when the displacement is maximum here. All right, and I'm afraid that is it for this session. All right, next time or in next lesson, of course, we will go through some questions, and of course we will do some calculations to see how it is done or how we can use Hooke's law. Okay, so till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.